All right. I'll begin with a word of prayer. Dear Father, we thank you for this day again. I thank you for this class and the break I just completed. Pray that you'd just help us to finish this semester well, Lord. In your name I pray, Lord Jesus. Amen. All right, so let me I have just like maybe 10 minutes of differential form stuff left, and then we'll shift over to kind of reviewing for test 4. So this is the definition of the integral of like a k form over a k-dimensional subspace. Basically, the deal is you need a parameterization of the subspace, and what you end up doing is basically evaluating the components of the form against the parameterization, and then multiplying by like the partial velocities of the parameterization, and that's how we set up the integral. And this thing I'm constructing here, as I show in the notes, it reduces to the line integral and the surface integral in the context of one forms or two forms. But it's other things as well. Like here's something that's a little bit further down the path. Let's say here's a 3 form in 4-dimensional space: t squared plus x squared, dx wedge dy wedge dz, right? And I look at a particular 3-dimensional subspace of 4 dimensions, which has got this as its parameterization. UVW is this and that and that. So basically here we're looking at some sort of volume that's in the x equals to 1 part of 4 dimensions. And so this particular 3 form only has one interesting component, like basically 2, 3, 4 is it. And so if I plug in 2, 3, the parameterization at that point, I've got x is equal to 1, and I've got, let's see here, I'm sorry, that's t equals to 1. I got to pay attention to my definition. I put t first, x second, y z is fourth actually. Okay, so this makes t equals to 1 and x equals to 2u, and that's why I've got 1 plus 2u squared, which is 1 plus 4u squared. That's my evaluating the form at the component. And then of course I need to multiply by the partial velocities in the 2, 3, and 4 directions, which give you this 2, that 3, and over here notice that this differentiates to wrong. All right, well, sorry. Apparently this needs to be 8w, right? Which means that probably should be 32 if I haven't made a mistake. Anyway, so to integrate it, I just integrate over the parameter domain and plug in the parameterization, multiply by the velocities, and that's how it works out. So now, like here's the specific details on how that definition sorts out for, a one form. Like I told you guys before, the one form integral is the line integral. The 2 form integral, no, this is just for 3 dimensions. In 3 dimensions, the 2 form integral is the flux integral, which is this. And that of course, you might recognize actually is the components to the normal vector field formed by taking the cross product of like partial x partial u, partial r partial u, and partial r partial v, right? Those are we're just taking essentially the dot product of the components of the corresponding vector field with the normal components. So like it should be familiar what that integral is. It's just that it's now an integral over 2 form. And then of course the 3 form is a little bit less familiar, but if you look at the 6 non-trivial terms of a 3 form and tilt your head and squint, you can see what that is like the Jacobian. So it's all tied into everything we've done this semester. It makes sense only because we have that change of variables theorem. So like it wouldn't matter how we formulate the form, we'd still get the same integral. Anyway, so I don't want to belabor the details here too much, just trying to give you a flavor of it. Now, the generalized Stokes theorem, I showed you guys last time, or the other time, that reproduces fundamental theorem of calculus for line integrals, Stokes theorem and divergence theorem all at once, and it also allows you to do interesting calculations that we wouldn't even encounter in this course otherwise. But like, as a follow-up to the one I just did, if I have that 3 form, alpha, right? If you look at this, you tilt your head and squint, you realize that I can rewrite that alpha as the exterior derivative of this particular 2 form. I don't really need a wedge there, by the way. This is a typo. So So this 2 form, exterior differentiates back to give that alpha that we just integrated, and I got 16, but I should have got 32 because I made the mistake, right? Anyway, so if I want to integrate alpha over m, right, where m is that 3-dimensional volume that I just talked about in 4 dimensions, well, generalized Stokes theorem says because that m is because that alpha is d beta, right, I can integrate over the boundary of m, which is something kind of horrible. It's actually a union of 6 different faces, I think, because it's a 3-dimensional. It's a closed 3-dimensional space inside 4 dimensions. It's going to have like 6 different faces. It's not a cube either because there's like a square in it, so it could have like a curved face. It would be whatever. Anyway, the point is there's 6 different surfaces that comprise the boundary of M, but the generalized Stokes theorem says that, oh well, that's just equal to, again, that should be 32. So I wanted to include an example in the notes that actually worked it out for something that was specific, and that's it. Now, I have not gone through the drudgery of actually calculating all 6 of those surface integrals to show you that it works out to 32, but that would be like the next logical step on that example. All right, so that said, I want to talk to you just about 5 more minutes and we'll be done with this. Maxwell's equations in differential form. So you guys, we've talked about Maxwell's equations. I've showed you how we can write Maxwell's equations in differential form, but we can convert them to the integral form using the Stokes theorem or the divergence theorem, right? Well, if you study, this is a typo. That's supposed to, first of all, be a vector, and that's supposed to also be minus. This is near and dear to me because I'm teaching that course this semester. But so anyway, there's a mistake there. But anyway, the point is, you can take these 4 equations and you can rewrite them as just 2 what are called tensorial equations. And what you do is you introduce something called the Faraday tensor. And it's a 2 form that has both the electric and magnetic fields in it all at once. The electric fields are in like the time-space part, and the magnetic fields are in the space-space part, right? But we get both the electric and the magnetic field simultaneously folded into this one object. And if you take the exterior derivative of the Faraday form, what happens, the mechanics of it, is that it has, the exterior derivative here has both time derivatives and space derivatives because this is a calculus of space-time. And so you get the curl plus the derivative, the time derivative of the magnetic field, the electric field. And over here you get the divergence of the magnetic field. So if you set this thing equal to 0, you simultaneously get this being 0 and that being 0, which are respectively Faraday's law and the no magnetic monopoles law. Yeah.
Is a tensor just a vector in 4D space?
A tensor is something more general than a vector. It has to, like, a tensor more generally is it's the abstraction of our idea of vector, basically. It's something we need to write equations of physics. Tensors, to say something's a tensor is to say that it transforms a very particular way with respect to coordinate change. And so you can write down one kind of tensor that transforms, let's say, what's called covariantly, and you can write another kind of tensor which transforms something called contravariantly. They're kind of inverse transformations. And so what this means is if you build equations with both covariant and contravariant things so that they're kind of balanced, when you change coordinate systems, that quantity remains invariant. So because the laws of physics have to be written in such a way that they're independent of our choice of coordinates, we need tensors to like formulate physical law ultimately. That's kind of baked into the cake of these things. These objects themselves are what are called geometric because they don't actually rely on a system of coordinates despite the appearance of it with the dt. But anyway. And then there's something called the Hodge dual. The Hodge dual, well, we saw Hodge dual. I told you about the Hodge dual in 3 dimensions. There's a Hodge dual in 4 dimensions that's it flips time and space and time. And anyway, so it basically, when you take the Hodge dual of the Faraday tensor, you get this thing called the dual tensor where the roles of the electric and magnetic fields have been flip-flopped. And when you look at the derivative of the dual to the Faraday tensor, you can set it equal to mu naught times the Hodge dual of the current form, and this gives you the other 2 Maxwell equations, namely Gauss's law and Ampere's law with Maxwell's correction, which is kind of cool. But that alone is not interesting, I think. I mean, both interesting enough, but so I thought, okay, well, this is fun. I have a way to write electromagnetics in space-time. What if we were to write it in time, space, 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 space? Like, what about if you had time with 4-dimensional space? What would Maxwell's equations look like in that context? I'm only really interested in one of them, the most familiar one, the one we spent the most time on this semester, the inverse square law, right? The Coulomb field. What's the analog of the Coulomb field? That is the electric field due to a single point charge at the origin, everything else being absent. So you just have a single point charge at the origin in four-dimensional space. What's the resulting electric field, right? So I can express that here by constructing the vector, well, excuse me, the one-form potential for the five-dimensional theory, and it's just that. And I do it with respect to this notion of what's called the metric, and this is how we build the field tensor in terms of the one-form potential. It's the same thing in 4 dimensions if you do it. So that's the natural definition. And then, of course, I need to take the Hodge dual of the electric part. And after a bit, I find my way to, this is basically Gauss's law in differential form. And then what I do is I integrate that over a 4-dimensional sphere and use the generalized Stokes theorem. And when I do that, I'm doing that down here. So I'm integrating Gauss's law over a 4-dimensional sphere. Then here I have the exterior derivative. So I trade that for the integral over the boundary. But the boundary of a 4-dimensional solid sphere is the surface volume, actually, which you could figure out the formula for from the Math Battle 3, the tricky part, the one that was lengthy. All the formulas you need to calculate that are in there. And it turns out that the surface volume is 2 pi squared r cubed. So I get 2 pi squared r cubed E is equal to q over epsilon naught. And there you go. This is Coulomb's law if the electric field spreads out in 4 dimensions rather than 3. Yeah. And so, I don't know. I try to show this to you guys when I don't know how to show this to calculus. You're very strong calculus 3. I don't show this every calculus 3. Don't tell the other calculus 3s. You guys are special. Wait a minute. None of you took calculus 3 with me before, right? Well, don't answer that. Don't answer that. Anyway, so this same calculation in 3 dimensions, you integrate over a ball. The surface area of the ball is 4 pi r squared, right? So you get E times 4 pi r squared is q over epsilon naught. That's the Coulomb field, the q over 4 pi epsilon naught, rho hat over rho squared, right? In 2 dimensions, you get 2 pi r times the electric field is q over epsilon naught, which gave us that the field for the infinite line charge, for example. But anyway, enough. Any questions? I can blather on about this, but I should probably get back to what I'll actually put on your test more likely. I will try to ask some differential forms question on the test Thursday, but it would not be part of the required credit, right? That'd be bonus. Okay, so you guys don't want to look at the final exam for linear algebra, do you? Not really. Probably not. All right. Here is a previous Math Battle 4. Maybe let's look at the problem before we look at the solution, yeah? If I can find it. I stole this from my brother, if you're wondering why the formatting's weird. He has more time than I do, so he makes things nice and pretty. Let's see here. So here is plots of vector fields A. The vector field's F. Now, my brother believes in the use of bold. I do not, because I don't know any way you guys can write bold for vector, right? And I need to take points off. If a student doesn't understand the difference between vector and magnitude, I need to address that, right? That's kind of a big thing in this course, to understand the difference between types of objects we're working with. Number, vector, very different, right? And so I don't like this notation. It should be vector F, but anyway, my brother uses bold because anyway, whatever. That's the textbook notation, right? Okay, anyway. So what do you guys think? Which one's which? And which one is not there? And how would you judge? So this takes us back to the beginning, right? Day 1. Talked about how to visualize vector fields, right? This one does what? It's always going up at the same rate, and it should be pointing to the left when it's positive, and it should be pointing to we should be pointing to the left when the y is negative, right? And it should be, the vector should be pointing right when y is positive. Is there anyone like that? Oh, C. Right. It's kind of hard to appreciate. They all have the same general vertical drift of 1 unit, but apparently that's the case. So I agree with you guys. This has got to be C. Is it conservative? How would we check if these are conservative or not? These are two-dimensional vector fields. Yeah.
Take the partial y of, I guess, f sub x.
You are telling me to do this, right? I think. You're asking, he's saying we should check if the y derivative of the x component is equal to the x derivative of the y component, right? Is their mixed partials equal? They have to be equal if it's conservative. This is to check, basically that checks if the curl, the z component of the curl is 0 if we were to extend these to be three-dimensional vector fields p, q, 0. Right, we call this the closed condition. So like, how about this one? Definitely not conservative, right? Because partial q partial x is 0, partial p partial y is 1, 0 is not equal to 1. We can agree? 0 equals 0, it is conservative. Also, by the way, this is just the gradient of 1/2 x squared plus y squared, obviously, so it's conservative, right? Yeah? This one is, if this one's conservative, that one's conservative, because if a vector field's conservative, its negation is also conservative. Prove that. And this one is, yeah, not conservative, because 1 is not equal to -1. Very good. So did you guys figure out which one's this? Is it any of them? I think this one's not here, and I think this one is that one. And that one kind of circles around. It's this one, right? Should we go back to the answers? Let's see if we won. Oh man, I got way too many things open. All right, let's like close a bunch of these. So we said, yeah, I think we got it. I will post this after class. I just haven't yet. But. All right, so the next question is, we have f of x, y, z is this vector field 10, x, y, z, e to the x, and c is a curve parameterized by t squared, t to the 4th, t to the 6th, where -7 is less than t is less equal to 9. He says set up, but do not evaluate the line integral. This is a nice question. I like to ask these kinds of questions sometimes too on the test, because it's a way of me checking if you know how to set things up without wading through where you made your mistake in the integral, right? Trying to decide, is this 80% partial credit, or is this 20%? Sometimes it's really hard to see where mistakes are made. This one, you just have the setup, right? So it's a nice problem. And so here's the deal. We take the vector field, right? And we plug in x equals to t squared, y equals to t to the 4th, z equals t to the 6th, which is why we got a 2 plus 4 is 6, 6 plus 6 is 12, t to the 12th, and e to the t squared, because that's the x, right? And what's this go? This is the velocity, right? So we take force dot the velocity, that's the line integral. And our velocity in this case is 2t, 4t cubed, 6t to the 5th. Great. And then of course we have to integrate from -7 to 9. Yep.
What is this like on the website?
No. Showing it to you now.
Can we see that? Can I see?
Yeah, I'll post it. That is my intention, to post it in the announcements here. Oh, I want to look at the solution. Oh, man. All right. So can we calculate the curl and the divergence here? I think we can do that, right? I'll do the divergence. The divergence is what? Like 3x squared over x cubed plus 1 plus sine of xz plus 5z to the 4th, right? The curl, I'm not going to try to do in my head, because the curl requires calc. I mean, the curl's tough, right? So I think that's what I just said, 3x squared over x cubed plus 1 plus this plus that, right? And the curl, of course, we have to take like y derivatives of the z component, right, minus z derivative of the y component, and then z derivative of the x component minus the x derivative of the z component, and there's the last one, which works out to this apparently. I will say this. One of the things that makes the curl, why is curl harder than cross product, by the way, guys? You ever think about this? Yeah, well, you have to differentiate, but like besides that, what's something you can always do with the cross product? Something you should do on the final for sure. You take a cross product, what do? You check your work, right? Dot product of the cross product with the two vectors that input must be 0, otherwise you did it wrong. I have no such luxury with the curl, right? So the curl, you just need to be careful, right? But anyway, how about this? We've got a line segment from a point to another point. Oh, how generous of my brother. He tells us it's a conservative vector field. That's so nice of him. Let's see here. And I was using quarter points because I was stealing his work, so I didn't want to like redo all the points. So I made his points into quarter points so they could still be points in the course. That's what the Q points are, if you're wondering about. It's very exciting. But anyway, so fundamental theorem of line integrals, we need to write down the potential for f. What is it? I think it's x squared plus zx plus zy squared. I think that's it. X squared plus zx plus zy squared. I think that'll do it. We can check the gradient of f is equal to f. Like, this is how I calculate the potential, guys. I've showed you rigorous methods, right? I've showed you ways we can calculate by doing a partial integration and substituting and working through it methodically, right? But that is so slow. Guessing will always beat it. What did I do wrong?
Do you need a y as well?
Oh, the 1. Yes. Thank you. As I was saying, you must check your work. So you guys check my work for me. Thank you. So that's the potential. That doesn't solve the problem, but it's an awful long ways there, right? Because then we can use the fundamental theorem. We just take f of the endpoint minus the starting point. That should be the line integral. How would we do it directly? We'd have to parameterize the line. Can you parameterize the line from that point to that point? I hope you can. Right? Let's look at the answer. All right, so, well, at least I had the y last time I did it, right? And then, of course, fundamental theorem of calculus. For line integrals, we take, if it's conservative, we can do this. All right. Now, the parameterization, what's he doing here? I'm taking the initial point, which is 0 and 1. And what's this 2, 0, 1? Where's that coming from? Right, it's the displacement vector from the starting point to the ending point, right? It's the difference of end minus start. And you should always check your answer with something like this, right? If I plug in 0, I get 0, 1, 1. Good. If I plug in time 1, I get what? 2, 1, 0, which I'm supposed to, right? So it works. Great. And then to calculate the line integral directly from the definition, here it goes. So I evaluate my vector field at the parameterization. I take the dot product with the velocity. I get this lovely thing. I integrate. I get 3. Okay. Which do you prefer calculationally? Like, obviously, if you can find the potential, that's the better way. But sometimes you have to do both because both are expectations of this course. So I want you to understand both. Oopsie. Don't look at those. Sorry. My bad. We should ask the questions before we look at the answers. So you guys, can you fill in the blanks here? We have a vector field, MNP. MNP have continuous partial derivatives of all orders defined in R3. fill in the blank and circle the correct answers. If the curl of f is equal to 0, then f is a conservative vector field. Why is that okay to say here? Because all of R3 is a simply connected set. So we do have curl implies conservative in that context. Be careful, it's not always true, right? If your domain was missing some kind of defect such that you could not deform a loop past that defect, then all bets are off. Okay, curl of f, 0 implies f's blank integrals are blank independent. Surface independent was never even a thing in here, so that's not it, right? So it must be path independent by process of elimination from discussion, right? And over here, what do you want? Line, right? The line integral is path independent. Path independence is a property of line integration, right? I mean, we call it line integral, but they're really curve integrals, right? Okay, fine. Divergence being 0 implies f. So actually, this is a defect of my course. I don't know. Have we talked about surface independent? I mean, I guess maybe we have. I should scale back a second. We have talked about this because we did the problems with like Stokes' theorem where I replaced the bounding curve with a different. We did stuff like, I'm like, okay, so it's the boundary of this, right? But it's also the boundary of this thing, right? So that's kind of a surface independent sort of thing. But the larger point here, actually we did talk about this. I called it the deformation theorem, and I said that the integral of df ds over S1 is equal to the integral of f dot ds over S2, where these are both outward oriented, right? Given that the divergence of f equals 0 between S1 and S2. We did actually talk about that. So to give that to give that a proper label, that's surface independence of the integral, if that makes sense. Okay, anyway, so to answer the question, divergence 0 implies the flux integral is surface independent. All right. Let's see here. So we have a counterclockwise oriented region of the bounded by y equals to 1 and y equals to 2 minus x squared. So that's a parabola that opens down, right? So it's got y equals to 1 as its base, and so like the picture looks something like this, right? And we're supposed to calculate that over the counterclockwise oriented boundary. Now, should we do this directly? The answer is obviously no. You don't want to do that directly. That'd be very tedious. Two integrals, right? This is a what problem? This is a Green's theorem problem, right? We should trade the integral around the boundary for the integral around the area integral of the corresponding closed condition difference. So like here's the details. Okay, so that's my p, that's my q. I got to do partial q, partial x minus partial p, partial y. And goodness gracious, imagine how tedious this would have been if you'd actually tried to do the line integral directly. It would have been horrible. But we don't. And these just work out to 2y, right? From that, this is gone. And all this junk is not is absent because when we take the x derivative of that, it's just 0, yay. And so, of course, this is a slightly interesting problem because we're still back in, like test 3, we don't get away from test 3. Test 3 is still with us, right? You cannot help but review test 3 to do test 4 because the only way we can actually calculate, surface integrals is to actually do, or sometimes either a double or a triple integral if we use the Gauss's theorem, So double and triple integrals are still with us. Obviously, you still need to know polar coordinate change and all that jazz, right? This one not so much. This is just straight up like type 1 Cartesian setup, right? We just have to iterate the integrals properly. Next question. All right, you've got a circle of radius 1 oriented clockwise. And you've got C2 also oriented clockwise. It's a upper half of a circle. And you got a line segment which is closing off the semicircle, so it's a diameter. C1's a diameter. We're given this two-dimensional vector field Mn, and it has continuous partials, and ooh, well, look at that. The difference of the x derivative of the y component and the y derivative of the x component is 4. All right? And we're also given information about the integrals around the edges, right? C2 and C3 we're given are pi and 5 pi. And, oh man, my brother's being very, very nice. He even told you the area of R is 7 pi over 2. Interesting. Huh. Wonder if he needed to tell you that. I don't think he really needed. You could have figured that out, couldn't you? I guess he must have given this test before, and the depression of having students not figure out the area of the punctured half circle must have weighed on him, so he just said, all right, enough. I will put the information here. They can't get it wrong. What he fails to remember is there are other students who will still think it's part of the problem to derive that. Those students also exist. Because I've seen this semester. I give students information, and then they work it out. I told them this, and then they're working it out, and but it's part of the problem statement. Why are you doing that? Not you guys. That's actually another class. So, anyway, did you guys see what we should do here? This is again a Green's theorem problem, right? So let's look at the solution. Now here we have to operate symbolically, right? We have no choice in the matter because we don't have formulas. So we really have to deal with the matter. So the integral around the boundary of R is the positively oriented boundary, right? So we have to go counterclockwise on the outside, right? Which means C3 is in the right direction, but C2 is in the wrong direction. That's why there's a minus here. So C3 plus that. Now, C1 is clockwise oriented, right? So if you're a little dude walking around C1, then the interior of the region in question is on your left. So it's given the right orientation to be part of the positively oriented boundary of this region R. So that's why there's no minus here, but there is a minus there. So that you got to understand. And all right, so this by Green's theorem is 4 dA, but we know that dA is 7 pi over 2, so 4 times 7 pi over 2 gives me apparently 14 pi. And put it together, 10 pi. I like that. This is a nice question. If you understand Green's theorem, you can do this. It's really just testing. What's the point of this question? Do you guys understand the point of the question? Right. Yeah, this is all about, do you understand how the boundary works for Green's theorem with a whole? Right. Have you understood that? Yeah.
How did he derive the area of R? So he gave it to us.
Oh.
How did you derive it?
So the area of the big circle, if it was the complete circle, would be 9 pi, right? Because pi r squared is 9 pi. So half of 9 pi is, 4.5 pi. But then you're missing that unit circle disk. It's been punched out, so you subtract pi from 4.5. That gets you back to 3.5, which is, in mathematician speak, 7/2. Yeah. So that's why I'm a little bit confused, why he gave that. I guess the point was he didn't want to test on whether or not people could calculate the area of a deleted half disk or something. But whatever. Okay, so let's go on to the next one here. I'm just going to show you the solution because we're almost out of time here. So here we have the upper hemisphere. Z is positive. S2 is the disk. So basically, we've got a half of a basketball, sort of, something like that. But here we're orienting both S1 and S2 upwards, right? And this time we're given that the divergence of F is Z, all right? And the flux through, notice that we don't have a formula for F, right? So pretty much we have to use the divergence theorem and piece it together with the partial information we have, right? So, all right. The boundary of E is the positively oriented outward or outward boundary, right? So S1, it's outward oriented, great, but S2 has got the wrong orientation, so we have to flip it. So the boundary of E is S1 minus S2. And so we get that minus that, which is equal to that. And then you have to do the integration because it's a sphere, so you use spherical coordinates. I would recommend definitely using spherical coordinates for a spherical problem, right? So there's that one. This one, let S1 be the surface parameterized by that. So what this is like a, oh. Huh. I think this is a cone, actually. But anyway, doesn't matter. We got these parametric formulas. They're given to us, right? We're told the parameter domain. So first order of business to find it says find both orientations for S1. I haven't emphasized this language in here, but I should. A surface, orienting a surface is simply giving a normal to the surface. I mean, we've talked about this, but I haven't emphasized as much as I should have this semester, probably. So, why are there two orientations? Well, you can either do n or minus n, right? You can either orient it up or down. If one's up, the other's down, right? And so, as I say here, if we calculate the normal using u first and v second, we've got the cross product of partial velocities in that order, which works out to this. But if we do the v first and the u second, then it flips the cross product and gives us minus. So those are the two orientations. Oh, look, I can check my work here. Yay. And then I said set up, but do not evaluate the surface integral. So, yeah. So we got that. Yep. So, yeah. Set up, but do not evaluate the flux integral. All right, so here we have a formula for f is given, z, y squared, 9 plus x. And so we have to, of course, plug in the parameterization formula for z in the first spot, and for we square the y formula in the second spot, and we 9 plus the x formula for the third spot, and we have to take the dot product of that with the normal vector field. That's how we calculate the flux directly from the definition. Yep.
Does it matter which normal vector field you use?
No. Well, actually, excuse me. It does say right there oriented downward. So yeah, it did. How do I know that's oriented downward? Yeah, because it's when we in this kind of language, like our default is to use z to define up and down. If in doubt, ask me what in the world do you mean by down, and then I will tell you. Okay, so. Centroid. Woo! All right. So find the centroid of part of the sphere in the first octant. All right. And so he's telling us that we need to calculate these four surface integrals, basically. All right. And so I think I just do them. I don't think, if you're in the first octant, it's not obvious that any of those, I think it's symmetric, so the x and the y and the z should all be the same, right? In the first octant? I think so. Probably I just have to do one integral by the symmetry here. Yeah. So 1, 1, 1. And then this one here, we have a solid cylinder, all right? And we have the boundary of it oriented outward. There's a vector field f, all right? Don't be afraid, though, because if you apply the divergence theorem to that, everything ugly there goes away, right? Because when you take the x derivative of the first component, you're just left with z. You take the y derivative of the second component, you're just left with z. You take the z derivative of the third component, you get nothing. So we just got the integral of 2z. And because it's a cylinder, I use cylindrical coordinates. right, and 8 pi. This one is a Stokes theorem, verify Stokes theorem problem, which means that you're going to have to calculate the curl of the vector field, calculate the circulation of the curl around the boundary. And this, I think this one has 2 boundary curves because it's got C1 and C4. And so you do that. And then you have to calculate the flux of that over the curl. Now, I have the details following this, but problem 13, got a vector field, find a function. So here is like a combination gradient curl. Find the vector field, which, you know, works it out. Find a potential or find a vector potential such that the sum of the gradient of G and the curl of B give you back the F. So when I see something like that, I kind of like divide and conquer. I look for the piece of the vector field, which is obviously conservative, right? So you look at this, and the thing that jumps out at me is the x squared, the y cubed, the z to the 4th. I can easily obtain those from a gradient of like 1/3 x cubed, 1/4 y to the 4th, plus 1/5 z to the 5th, right? Now the other things, they're not where they belong, right? Y, minus y in the x spot, z in the y spot, minus x in the z spot. Those have got to come from a curl, most naturally. So that would be my strategy for solving this problem. Anyway, so I will post the solutions to these. Here they are. Let's see here. Oh, anyway. So yeah, I will post these and the solution. So so just to talk about Math Battle is tomorrow, right? I mean, you guys don't want to take the test tomorrow, right? I don't want to give you a test tomorrow. So we need to think about teams.